And you might be thinking, what does area have to do with algebra or expanding brackets? What I want to suggest is that sometimes we can have things that look very similar, but are in fact, look things that are different, but are in fact very similar. I'll show you an example of what I mean. If I look at something like this, do you see a dog or a bird here?
I see both.
You see both.
I see two hands. As soon as I think.
What do you guys see? You can't see.
I see one hat. That's what I see.
Oh, I broke it. Let's try and move it that way. Do you see a dog or a bird for this one?
I hear brainstorm. Do you hear brainstorm or green water?
How about another one? What color is this guy? No, it's gold. That's gold. It's gold. It's obviously gold. Where are you guys getting blue and black from? So, two things that can look different but are in fact the same. This one over here, again, I could just do this out normally. I could say, oh yeah, I do the brackets first. That's 2 times 4, and that's equal to 8. I want to show you another way we can think about this. We looked at area on your do now, and I can actually split this up in terms of area, right? If we think about a rectangle, when we find the area of a rectangle, we know we have to multiply those lengths together, okay? So I'd have 2 here. What would go along my length? Well, I'd have 3 plus 1, right? Draw a little block like that. What's the area of just this part here? It'd be 2 times 3, which is 6. And then this one would be, 1 times 2, which is 2. If I add those together, I also get 8 as my area, okay? So one thing that we can think about, these numbers, we don't just have to calculate them. We can have a visual representation of what they actually mean. And I think that's really helpful for things like algebra. Because often students look at algebra and they're, oh, this is so conceptual. Like, what does x even look like? What's x plus 3? We can actually draw a rectangle that represents this. Why don't you try that for me now? Can you do the same thing I did over here? Right? I drew a rectangle that represented 2 times 3 plus 1. Can you now draw a rectangle that represents 5 times x plus 3? What would that look like? Try to draw that for me. I have a width and a length. If I have something like this, what is its width and length? What 2 things am I multiplying together here? Oh, I heard something. Max? 5 and x. So maybe like this. Is that what you're thinking? Yeah? Then notice something different. We're not just multiplying x though, are we? What are we multiplying? Go, Mia. X plus 3. So just like I had here, I had 3 plus 1. So I'm going to have x plus 3 here. Again, I draw my little box up. It doesn't have to be to scale, but this is just an idea of what's actually happening here, right? Now I can find the areas of these individual parts. What's 5 times x? That's 5x, because we put them together in algebra. And 5 times 3 is 15. Okay, well done. So what's actually happening is that when I am expanding, what does it mean to expand? Right? It means I multiply, because we know what brackets are, that's multiplying. But expanding is we multiply everything, on the inside by the outside. Can you write that down for me? We multiply everything on the inside by the outside. So here, let's check. 5 times x, that would be 5x. 5 times 3, that would be 15, right? And we can see that with a visual sense. And we can also just write it out algebraically. What's the problem when we get to this one? It's pretty tricky, you reckon? What's different about this one, maybe? Blake? It's a negative. So obviously, if I tried to do it for this one, I mean, it doesn't really make sense to have a negative area, because if I have 3 times m, that's 3m. But 3 times minus 2 is, what's that? Negative 6. I can't really have a negative 6 area. That doesn't really make sense. But this is just a representation of what's actually happening. I can still expand it out by multiplying everything on the inside by the outside. So 3 times m is 3m. 3 times minus 2 is negative 6. Now, I like to draw these arrows just to remind myself what I'm actually multiplying. Okay, if you're okay to do it without them, that's fine. Why don't you guys have a go at this one for me? I'll put a couple more up on the board. With these ones, always be careful. I know what expanding means. What does it mean? It means multiplying everything on the inside by the outside. And I'm going to draw my arrows there to make that really clear. Negative 4x times 2. A negative times a positive is a
negative.
negative. So I'm going to have negative 8x. But be very careful now when I have this one. I've got a negative times a negative, which is a positive. What's negative 4 times negative 1? That's 4x. So there is a 4. Let's do the coefficients. Let's do the numbers first. Negative 4 times negative 1 is just positive 4. But what's x times x?
X squared.
X squared. Okay, so sometimes they'll have multiple variables here, and so they'll be combining those. Not only are there numbers that we have to multiply, sometimes there are variables as well. We have to be careful. Remember, x times x, that gives me x squared there, okay? Right. And sometimes they'll have brackets combined with other things as well, and we can still do those. What do brackets mean again? Remind me.
You do them first.
All right, we'll do them first. I'm going to do these first. Can you expand these ones out for me?
So
3 times 2b. Yeah, you got it. And then 3 times 5, we know that. That's 15. Bianca, what'd you do next?
Then you add 3b.
Okay, so one thing that they'll ask you to do, not only are we expanding, we're also simplifying. We're also making it less complicated by grouping things together. So let's group the like terms together. I've got 6b plus 3b. Yeah, that's right. It's going to be 9b. Well done. Okay, we've got time. This one now, this one's a bit mean because they have lots of different brackets here. We can still do this though, right? It doesn't matter how many brackets there are, it doesn't matter what numbers or what letters we use, we can always use these same ideas. I multiply everything on the inside by the outside. I'm going to do that for this one first. So I'll have 2c minus, remember there's a negative here, so I'll have 6d here. What's going to happen here?
Times 5 minus 5.
Okay, so I've got negative 5 times 2c. Marissa, can you help me out? I've got negative 5 times 2c. So I notice a negative times a positive. What am I getting at? Negative, yeah, negative 10c in this case. And this one here, well again, that's a negative times a negative. So that's a positive 15d. Okay. Isaac, what are my like terms there? Yep, so look at the letters, right? Now, one thing that might throw you guys off is the kind of order of these. So you can rearrange these how you like, as long as you're doing them in the correct way. What's 2c minus 10c? Okay, so we've got a small positive number taking away a larger, and take away a larger number, so it's going to be a negative, so it's negative 8c. And then this one, what, negative 6d plus 15d, maybe it's easier if you think about it as 15d minus 6d, that's the same thing, and that would give me 9d, right? Can you see that? So sometimes if these are apart or in a different order, it might throw you guys off, right? But understanding that we can still group these because these are like terms. If you want to write them next to each other, that helps you understand it more, then feel free to do that. But you should have gotten this answer here, okay? Any questions about that? How do we feel? Not too bad? Okay. Now, this one's a bit mean because this is actually from year 9. But I think it's good to show you because we can actually use our rectangles to do this one. Did anyone have a go at this one? You know the answer.
Yeah, I know.
Sophie, can you tell me the first answer you wrote down? X squared plus 9. Now that seems reasonable, right? Because if I'm multiplying everything on the inside by the outside, I'll say, okay, x times x, x squared, 3 times 3, 3 squared, which is 9. How do we feel about that? Not good. Why not? There's something good here, right? We're multiplying some things on the inside by the outside, but there's something missing, isn't there? We didn't times them together. I think we're actually missing some, and this is why I want to draw the rectangle. Because if we draw the rectangle, it should actually be much clearer. In fact, this one's actually not going to be a rectangle. Does anyone know what shape this is going to be?
A triangle.
A triangle. Why do you say that?
Because it's 3.
What's my 2 side lengths? X plus 3 and x plus 3. If the side lengths are the same, what kind of shape is it? It's a square. Okay. So if I have a square that looks like this, sorry, my drawing isn't too great. What's the area of this one? X times x, which is x squared. x times 3, which is
3x.
3x. This one's actually going to be the same. Can you see that?
Which is 3x.
Now here's the hard one. 3 times 3, which is
9.
To find the areas, all we have to do is add those all up together, which would be, so this is not quite right, not what I'm looking for. On the right track though. But it's actually equal to x squared plus 3x plus 3x plus 9. And I know I can group like terms, and I can group that as x squared plus 6x plus 9. Why doesn't it make sense, Jackson?
So there's 3 and 3.
Mm.
And there's 3, there's a 3 and an x and a 3 and an x.
Yep.
But how come, so you got the 3 and the x
Yeah.
and the 3 and the x
Yeah.
and the answer. But how come, where did the x squared and the 9 come from?
Yeah.
It's like you make
Well, here's my 9. That's a good question. Here's my 9, and here's my x squared. Right? But when we were doing this, we actually missed these two. Now, I will show you a way later on in the year how to do it without drawing out this rectangle. But can you guys see how this makes sense, right? Yeah. We've got x plus 3, we've got x plus 3, and you guys realize it's actually a square, not a rectangle, right? And that's one way we can make sure we expand things out separately. So things that look different are in fact the same if we just rewrite them differently.